This is EC 201 lecture 28. So yesterday we were trying to figure out the CMOS inverter, and this is what we had. So let's call the dimension of the NMOS transistor W by L of the N, W by L of the P, VT of the N, and VT of the PMOS device. Okay. Yesterday we derived the circuit from scratch. Okay. Today let's spend some more time analyzing the characteristics of the CMOS inverter. Then we'll move on to the next topic. So if this was V in on the x-axis and V out on the y-axis, increasing the input voltage from 0 upwards until the input voltage reaches VTN, what do you expect? The NMOS transistor is cut off and the PMOS transistor is operating in the triode region. So the output voltage will do this. The same thing happens when you start from VDD and then go down. In this case, it is the PMOS transistor which is cut off until the input voltage goes below VDD minus VTP. Okay. And at some potential VG between this VTN and VDD minus VTP, both the transistors will operate in the saturation region, and at that point in time, the incremental gain, which is the slope of the characteristic between V in and V out, will tend to minus infinity. And before that, the NMOS transistor which was cut off gets into the saturation region and the PMOS transistor remains in triode, and beyond this high gain region, the NMOS transistor remains in triode and the PMOS transistor gets into saturation. And under what conditions will the slope here be infinity? RP and Rn become infinity, okay, which is equivalent to saying the lambdas of the two devices are 0. So, as I said yesterday, you can interpret this characteristic in many ways. If you are an analog designer, you would want to operate in that high slope region, because as an analog guy, you are interested in getting a lot of gain. As a digital designer, you would try and avoid this region as much as possible, because you define your logic levels as being, for example, you might want to define your logic levels as being a logical 0 if the input lies somewhere here, and a logical 1 if the input lies somewhere there. If it lies in the middle, that is not a legal digital level. And you can see clearly that when the input logic level is low, the output logic level is high, and vice versa. So this is the, in logic parlance, a NOT gate. And since we are primarily interested in this region, it makes sense to figure out what this VG is and what, let me call this V top and we call this V bottom. Since as analog designers we will be operating in this region, it makes sense to figure out, the attributes of this region. So how will I figure out VG? So as analog designers, we are interested in VG, V top and V bottom. So how would we find VG? We know that in this region, both the transistors are in saturation and both their drain currents are identical. So 1/2 mu n Cox W by L of the NMOS transistor times Vg minus Vtn the whole square equals 1/2 mu p COX W by L N times VDD minus VTP minus VGD whole square. It is WL of the PMOS transistor. I get rid of the half COX and I am left with VG minus VTN divided by VG minus VTN is nothing but mu P by W by L of the PMOS device divided by mu N W by L of the NMOS device, the square root of this guy, times VDD minus VTP minus VG. This is straightforward algebra, which implies VG times 1 plus square root of mu P by W by L of the PMOS device times mu N times W by L of the NMOS device must be equal to VTN plus VDD minus VTP times square root of mu P W by L of the PMOS device divided by mu N W by L of the NMOS device, which means VG is given by the absolute mess. And if you stare at this expression, it's quite straightforward, I believe, to figure out that this will be greater than VTN and less than VDD minus VTP. If VTN and VTP are fixed, is there some freedom you have as a designer in placing VG wherever you want? You know that this VG must lie in this region somewhere between VTN and VDD minus VTP, and we have this crazy expression for VG. If you didn't want to vary VDD or VTN or VTP, can you do something and change where this VG occurs? By fooling around with the W by L, you will be able to change VG. If W by L of the NMOS transistor is much larger than the W by L of the PMOS device, what happens to VG, do you think? Then VG is approximately VTN, because this chap is much larger than this guy, which means that this guy is much larger than this guy, so this expression will approximately go to 0, and similarly the same thing with this chap here. So the trip point of the inverter see, this VG is loosely called the trip point of the inverter. Why? I mean, below VG the output is high, above VG the output is low. So that VG is the point input voltage at which the output of the inverter is tripping. So this is often loosely called the trip point of the inverter. And you can see that if W by L N is much larger than W by L P, then the trip point of the inverter will basically tend to VTN. On the other hand, if W by L P is much larger than W by L of the NMOS device, then VG is approximately equal to VDD minus VTP. If the W by L's are comparable, then the trip point will lie between VTN and VDD minus VT. Straightforward. Okay. So, if you are indeed operating in this region, that means the input voltage is hovering around VG. What is the current flowing? VDD to ground. In this region here, what is the current? We have found VG, current drawn by the inverter. The drain current is simply 1/2 mu n COS W by L of the NMOS device times VG, which you have found from the previous page, minus VTN the whole square. This is straightforward stuff. Okay, the next thing to figure out is what are V top and what is V bottom. So how will you figure that out? Let's say VG is known because all the geometry is known, you have gone down the math, found VD. So if VG is known, can we find V top and V bottom? What is V bottom? It is the point at which the NMOS just gets into the triode region, and what is and when will that happen? V bottom is the voltage at which the NFET or the NMOS transistor just enters the triode region. And what is that? V bottom must be equal to VG minus VT N. The gate voltage is VG. The device is just entering triode. For an NMOS transistor to enter triode, the drain can go one threshold below the gate, and that's precisely what this equation is saying. And so, and the drain potential is V bottom, the gate potential is VG, and V bottom is VG minus VTN. Similarly, by the same token, V top is the voltage at which the PFET just enters the triode region, which means what now? For a PMOS transistor, the limit for threshold is defined as the drain can go one threshold above the gate. Okay, so V top is nothing but VG plus VT P. So given the geometry of the transistors and their properties, you can figure out everything that you wanted to know about this curve. You will be able to calculate VG, you will be able to calculate when this infinite slope characteristic ends on the y-axis. So if you wanted a large incremental gain, input must be riding over this VG. You have to somehow find VG and then add your small signal around it and then give it to the inverter. This, by the way, as I discussed, is this chap here, as I discussed yesterday, is the symbol used for the CMOS inverter. It is the same logic symbol that you used earlier. If you are dealing with analog work, there is no confusion, so there is no problem in using the inverter symbol. So one obvious question is, how do I find VG? Any suggestions? I gave you an inverter in the lab. I said, hey, tell me at what is the trip point of this inverter, or what is the input voltage at which you see this high gain characteristic. So can you tell me what you will do? There are many ways of doing it. Can you, by now I guess you should be able to give me one solution which works. Friend here says, so he takes this inverter like this, he puts a voltmeter here, he's got a variable voltage source here. So he reads the voltmeter reading. If the voltmeter reading lies between V top and V bottom, then whatever voltage is applied, so he has applied a voltage Vg, he reads the output of the inverter using a voltmeter. If the voltmeter reading lies between V top and V bottom, what is the conclusion? He is done. So it tells me whatever Vg is there here is the right value. Okay. Now if the voltmeter reading is too low, let's say you know V top and V bottom for the time being. I mean, that's a circular argument, because to know V top you need to know Vg. If the voltmeter reading is too low, what does it mean? If the voltmeter reading is too low, you must decrease Vg. If the voltmeter reading is too high, you must increase Vg. Does it make sense? The question now is, how do you know V top and V bottom? You don't. Okay, so can somebody suggest an idea that will work? What he is pointing out is, I mean, if I knew V top and V bottom in the first place, I'd give you Vg right away. There's no need for this experiment. This is V top. You don't know the exact value here. This is V top. You don't know this exactly. This is V bottom. You don't know this exactly. But you know that this will be close to VDD. This will be close to ground. Okay. And any value of the voltage between V top and V bottom is good enough. So the suggestion is to compare this voltage. A safe bet is to just compare it with VDD by 2. And go and tweak Vg based on the difference between the output voltage and VDD by 2. So if the output voltage is greater than VDD by 2, what should I do? So if the output voltage is greater than VDD by 2, that basically means that you are operating somewhere here. What should I do then? That means Vg is too small, so I must go and increase Vg. On the other hand, if the output was smaller than VDD by 2, it means that Vg is too high, I must go and reduce Vg. Is this clear? You should be able to tell me what are the signs in the op-amp. Left is positive, right is negative. And if this is an ideal op-amp, once things are settled, this V out will be equal to VDD by 2. Is this clear to everybody? The output voltage of the op-amp will be Vg. So that kind of finishes the discussion on the CMOS inverter. So far we have seen NMOS transistors, we have seen PMOS transistors, we have seen how to put those two together, and putting the two together is very advantageous because the NMOS and PMOS transistors are complementary in some sense. You can do nice things like have an active load where you can get a very large gain without having a large resistor, alright, or you can have a CMOS inverter which gives you in principle a very large gain without any additional bias network at all. As I said, having the PMOS device is very nice because the NMOS device acts like a current sink, so it will suck current out of a node. A PMOS device will act like a current source, it will push current into a node. So they work very nicely, and it is possible to make NMOS and PMOS transistors on the same chip, and this technology is called CMOS technology. And it turns out that in practice the mobility of holes is less than that of electrons, so mu p will be much smaller than mu n. In fact, typically it's about a factor of 3 smaller. The same gain using a PMOS transistor, the PMOS transistor has to be 3 times larger. The GM is mu n C ox W by L times VGS minus VT. And for the PMOS case, it is if you want to have the same gate overdrive, which is the source gate voltage minus the threshold VTP, then the size of the PMOS transistor has to be 3 times larger to give you the same GM as an NMOS device. PMOS transistors are very useful, especially when you want to make current sources.